Okay, we'll start from the current slide. I may even turn on the projector. I don't know. Sorry, we're late getting started, but the only major announcement I know about, and it's not all that major, well, there may be others. Let me check this too. I've only received one paper and one test. So 2 of the 7 students have turned something in, okay? And I don't know if they've asked for midterm progress reports yet or not. I haven't checked emails much this week at all. I didn't see it when I checked earlier. And if so, I'm going to have to put down something that's not too favorable there. But, okay.
I have my test in today.
Okay, great.
I have my test in.
Okay.
How
All
long
right.
will you be here today?
What's that?
How long will you be here today?
I'll be here till 6.
6. Okay.
Yeah. Now, I'm in class from 1:15 to 5:45, so you can either bring it here or slide it on my door downstairs.
Okay.
Yeah. Okay. Now, second thing was office hours tomorrow. Usually on Fridays, I'm on the Birmingham campus, 8 to 12, office hours. However, tomorrow I have an eye appointment right across the street here, so that's at 8:15. So I probably won't be on the Birmingham campus, definitely at 8:15, nor will I be there probably at 9. Could possibly be there as early as 10. Maybe a little before, possibly after. I don't know how long they're going to take across the street here. So I will be, I'm guessing, I'm going to shoot to try to get there by 10 o'clock if I can, but it's completely out of my control, mostly anyway. So anyway, but sometime around 10ish or so, till noon at least, I'll be there. Maybe longer. Usually I'm there longer, but I don't want to be too late because I'm supposed to take my vehicle for service tomorrow afternoon, so I can't stay around too late or else the shop will be closed. Okay. Any questions on anything we've done so far? Okay. We are in Chapter 2, Matrices, 2.4, which is elementary matrices, and we're doing example 4, top of page 78 now. It says, find a sequence of elementary matrices whose product is the non-singular matrix A. Let me get my pen set up. Okay. Matrix A, which is -1, -2, 3, 8. Now, they told us it was a non-singular matrix. In a 2x2, it's really easy to tell if a matrix is singular. Okay, therefore pretty easy to tell if it's non-singular. For it to be singular, that means one of those rows or columns depends on the other. Okay? So you can look at that and see that, no, one is not a multiple of the other. Okay, any way, shape, or form. The other way you could do it, if you didn't remember that, you could just do the determinant. And remember we did that earlier, didn't we? Mm-hmm. Yeah, and that's be -8 plus 6, that's not 0. So we know this is a non-singular matrix. Now we didn't have to do that, but it's just for a 2x2 it's so easy to check. Okay, they told us it was non-singular. Okay, now what they're asking for is a sequence of elementary matrices whose product is this. Now, what we did last time, and have been doing up till now, are finding the elementary matrices that row reduce this. But that's not what this is asking for. This is asking for the series of elementary matrices whose product is this. So what we're going to have to do is do the first thing, which is find the series of elementary matrices that row reduce this, and then do their inverses in reverse order, and that will then be what will produce this matrix. It sounds a little convoluted, and it is, okay? But let's see what we're going to do here. First, what would be the first step you'd want to do to row reduce that?
Would it be make the negative one and positive one?
Yes, but you can't just make a single number.
So I have to divide by negative one.
Okay, divide what by negative 1?
Divide negative one by negative one.
Divide what by?
Negative one.
Okay, you can't just do a single number. You have to do an entire row.
Oh, okay. So by negative one and negative two.
Yeah. Divide row 1 by negative 1. Or how about multiply row 1 by negative 1? That works too, right? So what we're going to do is minus row 1 becomes the new row 1, right? That's easier to write that way, okay? So that will then produce 1, 2, 3, 8. But what's the elementary matrix that did that for us? What is your E that did that very thing?
What is that? What am I doing?
I'm sorry?
Would it just be divided? Oh, multiply?
Okay. What is the elementary matrix?
In the same row.
It's what?
In the same row.
Okay. An elementary matrix is a matrix that is one elementary row operation from the identity matrix. So if you did the same thing here to I, and let's go and write I up here. The book does it. It always seemed like to me it would make great sense to do that. What is the identity matrix that's the same size?
It'd be square, right?
Yeah.
Square identity matrix. So it'd be 1, 2.
Identity matrix.
1, 0. Right. 1, 0, 0, 1.
That's it. Okay. Diagonals are 1. Everything else is 0. Okay. Now, if you had done the same operation there to that matrix, what would be the result?
The same operation for it?
Yeah, same operation you did here, do it to the identity matrix. What does that give you?
Oh,
Negative 1,
0,
0, 0, 1. Right. You just did it to the top row. Okay. Now, what we need to also keep track of is the inverse of that elementary matrix. Okay? The reason is to reproduce A, we're going to need those inverses. Okay? Now, what is the inverse matrix to this one? That if you multiply that by this, you would get that. In fact, how do you undo what you just did?
That's squared.
Say again?
Squared. It's squared.
Yeah, of course it'll be a square matrix. It'll be the same size. Okay, but what would be that inverse elementary matrix? Which itself will be an elementary matrix.
Right.
What undoes that to get you back to there?
The size. The middle size. So
Yeah, so you just do the same thing again. This will do it. Minus 1, 0, 0, 1. Now, if you don't believe it, try it. Okay? Try to multiply these two together. So you do, which is 1 plus is 1. 0. Zero. Okay? That did it. That will do it. All right. Now, the book didn't do this. I thought thought it would have been a smart idea to do that. The book didn't start off here. I think that's a smart way to start here too. And then you just do the same operation here to get there. Okay? Now, the next line's going to be a little, okay. What's the next thing you're going to do to get this to reduce row echelon form? Yeah. What you want to happen next? You wanted a 1 there, you got it with the first step. What you want next? 0 there. How do you get that to happen? Oh yeah, that would always make, but that make the whole row 0. Okay, and we don't want that. We want it in to come out being an identity matrix, not a 0.
So when you subtract by 3?
Okay, close. Minus 3 times this added to that, right? Okay. Remember the 3 elementary row operations. Multiply or divide a row by a non-zero number, like you did. Multiply by -1 or divide it by -1. Okay, that's one. Another one is exchanging any 2 rows. That's perfectly fine to do. Okay? And the third one is adding a multiple of 1 row to another row. So we're adding -3 row 1 plus row 3. So let's write it down. -3 row 1 plus row 3. And that becomes the new row 3. So what would that be then? Top row stays the same, 1, 2. Mm-hmm. 0. That's exactly what we wanted. Okay? Now do the second term. Is what? 2. Perfect. Okay? So, what elementary matrix would do that same thing? Now this time, don't look at this one over here, look at the one up there. What would you do to the identity matrix, doing that same step we've written here, but do it to the identity matrix up there? Just like the first row stayed the same, that first row stays the same. Huh? I'm sorry? Oh, I'm sorry. Okay.
So will we subtract by 2?
Okay. Do the same thing this how you do it, but only do it to the top matrix. -3 times 1 plus 0. Huh? -3 plus 0. -3. Okay. And then?
So we did, I'm just going.
You're doing this operation to the identity matrix. Okay? -3 times 0 would be 0.
Right.
Plus row 3, which is 1. 0 plus 1 is 1. All right. Now, see if you remember this one. What is the inverse matrix for one you just did here to get you there? In other words, the other way to look at it, what undoes that?
The sums.
Second?
Sums. You multiply the Change the signs?
It would be this thing here, except rather than multiplied by minus 3, multiply by positive 3. Okay? Because if you do positive 3 times 1, that would become 3 down here. So it'd be 1, 0, 3, 1. Okay, that's the inverse matrix. Okay. Here's how you check it. 1 plus 0 is 1, yes. 0 plus 0 is 0, yes. Negative 3 plus 3 is 0. 0 plus 1 is 1. Okay. Turn back one page and you'll see, oh, you don't have your book with you. You'll see what those rules were. And let's do it again. If you exchange two rows, you exchange the same two rows. So they look identically the same. Okay? If you multiply like we did here, it's just changing the sign that you're multiplying by. Okay? So it'll only differ by a single sign, not a whole row sign, just a single sign. And if you're multiplying or dividing by a number, you divide or multiply by the number. Up here, we multiply by minus 1. Down here, we either divide it by minus 1, or if we divide it by minus 1, up there, you multiply. So if that would have been a 2, if we'd have multiplied by a minus 2 there, you would divide by minus 2 here. So the multiplication and division is a reciprocal relationship. The exchanging two rows is the same, and adding by a multiple of one row, just add the opposite multiple of that row.
Would that be only taking the inverse of it?
Okay.
Or
yeah, and taking the inverse of an elementary matrix.
Okay.
Only elementary matrix. So when you're exchanging two rows, you exchange the same two rows back together. When you're multiplying or dividing by a number, it's like if you multiply, see, with negative 1, it's really easy. Multiplying or dividing by negative 1 is going to be the same thing. But if you multiplied by 2, then you would divide it by 2 for the inverse. If you multiplied by negative 1/3, you would divide by negative 1/3, which is multiplying by negative 3. So the sign stays the same, but it's the multiplicative inverse. Here, the sign changes. And that's all that happens. On the one that got changed, that sign changes. On this one, it's the reciprocal, but the sign stays the same. And on changing two rows, it just changes two rows. Okay. We didn't do that. Okay. Now, what do we want to happen next? Okay, we're doing with this one. What's the next thing we want to happen?
The 2.
This 2?
Yeah.
Becomes a
1.
1. How do you make that happen? Divide by 2 or multiply by 1/2. Either one you want to do it. So I'll just do it that way. Row 3 divided by 2 is the new row 3. Okay? So I'm running out of room like crazy down here. This will be 1, 2, 0, 1, right? Okay. What elementary matrix would have done that same thing? The top row stayed the same, so that's a 1, 0. Do this operation to that. Go! Do this operation to your identity matrix. This operation to the identity matrix. 0. Not 1. 1/2. divide it by 2. Divide 1 by 2 and you get 1/2. Right? Okay. Now, what is the inverse elementary matrix that would, what's the inverse of that one? 1, 0, 0, and 2. When you, this one's divided by something, you multiply it by the same thing. Okay? If you're multiplying and adding, then you multiply by the opposite. Okay? But if you're multiplying or dividing, you divide or multiply by the same thing. So this one's dividing by 2, this one's multiplying by 2. Check it and see. 1, 0, that's 1. 0, 0, that's 0. 1, 0, that's, I'm sorry. 0, 0, that's 0. And then 0, 1/2 of 2 is? That works. Now, unfortunately, I need another room on the page, a block on the page. Don't have space to do it, but let's just say what it is. What's the next thing you want to happen? To make this an identity matrix.
So I need 2 to become but I need 2 to become 0?
It becomes 0. How do you make that happen? Huh?
Subtract.
Okay, yeah. Multiply this one by -2 and add to that. Okay? So what do we just say? -2 row 2 plus row 1. That's what you do. Okay? Now, we know what this becomes, right? Whoa! Okay. I don't have much room, so I'm going to squeeze it in here. Okay. I'm using the bottom row, so just write that down. Okay? Okay? Now, -2 times 0 is 0 plus 1 is 1. -2 times 1 is -2 plus 2 is 0. So you've got your identity matrix there. Okay. Now, we need to do the elementary matrix that does the same thing that does. So here's the next elementary matrix. Sorry, I don't have much room here. But what did we do? Multiply -2 times row 2 of that one and add row 1 to it. So again, we're not changing the bottom row, so that stays 0, 1. This 0, 1, not that 0, 1. Okay. And we're only changing the top row. We do that by -2 times 0 plus 1 is 1. Yeah, that stays the same. And then -2 times 1, we're using this row down here. I mean, that row down there. -2 times 1 is -2 plus 0 is -2. Okay? So that's the fourth elementary matrix. This is E1, E2, E3, and this is E4. This is, This is E1 inverse, this is E2 inverse, this is E3 inverse. I'm sorry, that's not writing well. Okay, we need E4 inverse. Okay, what will it be? Okay, 1, 2, 0, 1. You're absolutely right. Okay. Wait. Yeah. Okay. Yeah. Because all you're doing is change the sign. We can check it quickly. That would be 1 plus 0 is 1. Good. 2 minus 2, 0, that's good. 0 plus 0 is 0, and 2 plus 1. Yes, that works. Okay. Now we've got our 4 elementary matrices that did the same thing that these did. We've got the inverses of those matrices. So what we do to get, and this is your answer, okay? It says find a sequence of elementary matrices that can be used to write the matrix A in row echelon form, okay? Okay, I'm sorry. I misread the problem. Sorry. Okay, we didn't need to do the inverse matrices there, but it's okay. Okay. So what we have, okay, it says find the sequence of elementary matrices that can be used to write the matrix A in row echelon form. So basically you started with A, that's this thing here, and the first thing you did was multiply this one by E1, which is that one, and then to that you multiplied by E2, and by that you multiplied by E3, and by that you multiplied by E4. Okay? So that is a series of matrices that you have. Wait a minute. I'm on the wrong page. No wonder that I said, this is not the same problem. I'm sorry. I said, how could I have gotten it that wrong? And it wasn't that I got it that wrong. I flipped the page to show you something I forgot to flip back, and you didn't have your book anyway. All right. Okay, now wait. It says find a sequence of elementary matrices whose product is the non-singular matrix that. Okay? These, the E1, E2, those are the ones you multiply by A to get to the identity matrix. Okay? So what you do to get to this matrix is multiply those in reverse order. Okay? So what you would do, and I should have left the thing on there, what I just had, we got that A, when you multiply by E1, E2, E3, and then by E4, these 4 here, that gives you the identity matrix. That's exactly what you got here, right? Okay. Now, what it's asking for here, find the sequence of elementary matrices whose product is this matrix. So we want to wind up with this. So how do we undo what we've just done? Well, if we undo this by multiplying by E4 inverse, then this goes to the I matrix. Well, now, I'm not going to write the I matrix down again because it's just the identity matrix, okay? So basically what I've done is multiply by E4 inverse, okay? Times the identity matrix, that's over here. So I did write it down, okay? But that doesn't change anything. Multiply by the identity matrix still, okay? That wipes out that. But then, what's left, you can multiply that by E3 inverse, and that will wipe that one out. So multiply by E3 inverse. And then multiply by E2 inverse, and that will wipe that one out. So E2 inverse. And then finally multiply by E1 inverse. And that will wipe that one out. Okay, so if you were to take these in this order, E1 inverse times E2 inverse times E3 inverse times E4 inverse, you'd wind up with that matrix. Now, if you want and C? Just to prove to yourself it will? Okay. So let's first do these two. And I'm going to try to do it in the space we got. So we're going to, this first matrix here is going to be the product of these two, E1 inverse times E2 inverse. Okay? So it'll be -1 plus 0. That'll be -1. Okay? Yeah. Okay? Now we'll do first row, second column. 0 plus 0 is 0. Okay? Then 2, 1 will be 3. Okay? And okay. All right. That was E1 inverse times E2 inverse. Now we multiply that by E3 inverse. So multiply this by that. But we do this one on the left, because we did those two first. So this is, that one's on the left, this one's on the right. Okay? And it's going to give us, I'm sorry if this is sort of crowded here, but it is. So this is going to be the rows, these will be the columns. Okay? So you're doing this product, which is that. Times that. So this is a -1. The 0 is a -1, right? Okay? Then you've got row 1 by column 2 would be 0, 0. Okay. Still stuck with the 0 there. Okay. Okay. And now the 2, 1 entry, this second row by this first column.
It's 3 and 1. 3 and 0.
Yeah. 3. Ah. Okay. And 2, 2 would be
0. 2
is 2. Okay. All right. So that's the product basically of those three. Now we're going to multiply that by E4 inverse. Okay? So the one up here is going to be the left hand, this is the right hand. So this is going to be is -1. Okay? Which is sort of good that it is. Okay? Then we're going to do that first row by the second column here. -2, which is a good there again. Okay? Then the 2, 1 entry is going to be second row by first column. 30 plus 0 is 3. Okay? That's very good too. And then the 2, 2 entry is second row up here by the second column here. Plus 2 is 8. Looky there. You just came up with a series of elementary matrices whose product is exactly that thing we started with. Okay? And that's how you do it too. Okay? You do the elementary row operations on A to reduce it to the identity matrix. While you're doing it, do those same operations to the identity matrix to get your elementary matrices. Remember, you always go back to the identity matrix to do it. And every time you get one of these elementary matrices, do its inverse. Remember how to do those. Do equal, do the inverse. And then, because you did these in the order of E1 times that, then E2 times the product of that, then E3 on that, and then E4 on that. To undo that, you start with the E4, and then the E3, and then the E1 inverses. So those go back to that order.
So the steps are you go from what's given, which is the 80, to the identity matrix, to the elementary, to elementary inverse. Is that right?
Yeah. If I understood what you were saying right, that sounded right. Okay? And sure enough, they just showed it in the book. We actually did it. Okay? Now, they say, of course, if A is singular, there's no such sequence exists because you can't get a singular matrix out of a series of identity matrices which are non-singular. Okay. So here I think we get to, can I erase all this now? Okay. Theorem 215, equivalent conditions. If A is an n by n matrix, square, okay, then the following statements are equivalent. Okay, all these are equivalent to one another. Now, I don't know if you remember, we started with just 2 or 3 of these, and ever since then we've added one more every now and then. So here, A is invertible. Okay, certainly if that hadn't been a square matrix, you couldn't have an invertible matrix. But not all square matrices are invertible. All invertible matrices are square, but not all square ones are invertible. But if A is invertible, then all the rest of these are true. Okay? The second of these that we did later is that A times some vector x, unknown vector x, equal to some known vector b, has a unique solution for every n by 1 column vector B, or they call it column matrices, column matrix or vector. Okay? So in other words, if A is invertible, then if you do A times some variable matrix of the right size, you can get a B, no matter what B is here, you can always, every one of them will have a solution. If B is a 0, then the x's are 0. It's the only way it can be. Okay? If B is anything else, then the x's, there is a solution for every B you see. There aren't any B's you can put in there that would not give you a solution, a unique solution. And that's because A is invertible. Okay? And so if it is invertible, do A inverse by this, you get x, and A inverse times that, you get a unique solution. Okay? So, that's 2. If that's true, A is definitely invertible too. So it goes both ways. 3, this is what I just said. A times x equals 0. Okay? Now, this is tough. They just write the number 0, but it looks like a capital 0, but that has only the trivial solution. Meaning x1 equals 0, x2 equals 0, x3 equals, all your x's are zeros. Okay? So if that's true, then the next one's true, then the upper one's true. If any one of them's true, the others have to be. So here's number 4. A is row equivalent to I sub n. In other words, you can do a row reduction on A and always get the square matrix I sub n. Remember, A has to be n by n, so that's, of course, the size you get. But if it's invertible, it is reducible, okay? And vice versa. It goes both ways. And then the final one, that's the one we just now have discovered. A can be written as a sequence, as a product of elementary matrices. Okay. That's the one we just discovered. It can be written as a product of elementary matrices. It's got to be invertible. If it's invertible, you've got to be able to do that. Why? Because you know this can be reduced to the I matrix, the identity matrix. Well, every step that you use to do this row reduction, you do those to the elementary matrix, to the identity matrix. That gives you the elementary matrices. Do the inverse of each of those in reverse order, and you've got A. So it's doable both ways. All right. Now we come up on sort of a new idea, but it's not totally new. Well, sort of. At the heart of the most efficient and modern algorithms for solving linear equations, linear systems, AX equal B, okay, whereas they bold, I put arrows over them, okay, is the LU factorization. Okay. Again, at the heart of the most efficient and modern algorithms for solving linear systems, that's the L. Oh, goodness gracious, be still my heart. Okay?
You haven't seen me, I've been here.
What's that?
I have been here.
I realize that. No. Yeah. All right. And I was saying to Terrell, when I looked and saw that I'd already marked the roll for this class today, I said, what in the world happened? I realized I was back one page. At the bottom of this page is Math 237. At the bottom of this page is Math 227. And the only two people who were here yesterday in 227 were two people who were also supposed to be here today in 237. So I marked the wrong roll, and neither one of them has shown up today, but both of them was here. So I had to go back and mark that roll for here, and I'm changing the roll now. So, of course.
Yesterday you said?
What's that?
You said yesterday?
Yesterday I taught 227.
Oh.
And it's at the bottom of the previous page from 227, 230. It has almost the same numbers. It has exactly the same number of students, 7 students in each class. Yeah, in each class. Vince was the first one in both classes, and then Daniel was in both classes. They were the only two here yesterday, so I marked the roll for today, not realizing I was marking the wrong roll until Terrell came in, and I turned to it and said, I've already marked the roll, and you're not here. Yeah, no, I'm sorry. Why? How can this be? Okay, so we're going to lead to what we call the LU factorization, in which a square matrix A okay.
Is that a partial?
What's that?
Is that a partial? What's the partial one? Is that A what?
AX equal B.
Oh, it's X. Okay.
Yeah, you're making fun of my writing.
No.
I can tell I'm not hurt by it at all. I'm used to it. Yeah. Okay. Daniel, yesterday when you and Vince were here for 227, y'all are both also in 237. I was on the wrong page. I marked you on the roll today because both of you are on both rolls. And when Terrell came in this morning, I said, I've already marked the roll today. How can this be? So I had you down yesterday. In today's class, I didn't mark you yesterday, so I've gone back and changed it. So, okay. So, here's what an LU factorization is, in which a square matrix A is expressed as a product is expressed as a product. A is equal to LU. Excuse me. Okay. Now, what are we talking about there? Okay. L is what we call a lower triangular matrix. Okay. U is called an upper triangular matrix. Okay. Now, what do we mean by these two terms? Okay, I'll give an example without real numbers, just representative. Here is a lower triangular matrix. A11, 0, 0, A21, A22, 0, A31, A32, A33. That's a lower triangular matrix. The lower triangle is all numbers. The upper triangle is all zeros. This is the lower triangular matrix. The diagonal is the diagonal, whatever it is. But everything below it are numbers, everything above it is zero.
Are those numbers like ones or they
any numbers? They can be fractions, decimals, rational, irrational, any real numbers. Okay. But up here, it's got to be zeros. Now then an upper, this is a lower triangular matrix. An upper triangular matrix would then look like this. A11, A12, A13. Tell me what else to write. 0, A22, A23, 0, 0, A33. Perfect. That is an upper triangular matrix. Okay? The diagonal and above are numbers. Everything below the diagonal is zeros. It can be any square size. Okay? So, with that in mind, let's formalize that, you might say, by the definition. Okay. If an n by n matrix, meaning square, okay, A, can be written, okay, left off the first word, yeah, all right. That's the zero. It was bizarre when Terrell first came in. I said, I've already marked the roll in this class. How can this be? I couldn't find it. What had happened yesterday, 227, the two of you were here, but I marked the wrong page here because both of you are in 237 also. I marked everybody else absent, which were these guys, because I was marking the wrong one. So I've got it corrected now, okay? Or in the process of correcting it. Still waiting to see if anyone else is going to come in. So if you have an n by n matrix, that's a square matrix A, if that can be written, yes ma'am. As far as I know, have you heard anything on the weather? Okay. What I would suggest is go to the front desk and see if they know anything.
Okay.
Yeah.
If I want to be still here, I just asking you because it's like a state of watch back.
What's that
It
again?
was a state of watch on our Gmail. That's why I was asking.
Oh, was there?
Yeah.
Okay, wait.
There was a tornado warning a few minutes ago.
Okay. All right. Now, is that a Cougar alert? Did it come through the school?
Yeah.
Yeah, they did a call and a text.
Okay.
We in danger right now.
Okay. But have they canceled school? Does it say that?
They just gave one.
Right. It's a
No,
warning.
this, okay. I can't remember which is which.
Students
Is watch less than a warning or warning?
Well, I'll be ready when you're ready to teach. But at the same time, I was just saying, is counselor not? You know,
Okay.
I'm just waiting on class.
What I would do, I would have to go to the front desk and ask them if they've heard anything. So you ask them and
I'll come back.
yeah, okay.
Y'all need to do that.
All right, thanks. I was afraid of this today because my wife said this morning, it could be some pretty rough weather about the time you're going to be trying to come home tonight. Oh, goodness, it was, actually yesterday afternoon was windy.
It's been pretty windy since like
Yeah.
It's a national weather issue. So
Yeah.
it's a national weather issue. So I don't know if they might cancel school classes or whatever.
Yeah, but we haven't been canceled yet, right? Okay. Just keep an eye on it. If you get anything, let me know. Okay. So if you got a square matrix, n by n, matrix A, if that can be written as a product, of a lower triangular matrix and they call it L, and an upper triangular matrix U, if it can, then we call this A is equal to LU. We've already assumed it can be written as this. We call this the LU factorization of A. Now, if you think about it, in math, if you have a polynomial expression or any other, trig, any other, that you can break into factors, then you can usually solve them more easily by dealing with each factor, right? Well, if A is a n by n matrix that you can write as a product of a lower triangular and an upper triangular matrix, we call that the LU factorization. You basically just factored the matrix A into a lower triangular times an upper triangular.
I'll give you an example.
Okay, we're going to. That's coming right up. I'm glad you asked. All right. Excuse me, I got the hiccups too. Okay. So if this is okay, I'll erase this. And here is a matrix. Okay. 1, 2, 1, 0. Okay. Now, without telling you how they got it, they say here is a product. 1, 0, 1, 1 times 1, 2, 0, negative 2. Now, they didn't tell you how they got that, but this is really simple. This is a lower triangular matrix because the thing above the diagonal is all 0. There's only one thing up there. And this being a 2 by 2, the diagonal is here. The only element below that is a 0. So that's the upper triangular matrix. Really simple. Let's see if indeed this is true. Do the multiplication. 1 plus 0 is 1. That works. 2 plus
0,
is 2.
1,
Plus
0,
is 1. And
2, negative 2,
is 0. Yep. Because this matrix could be broken into a lower triangular times the upper triangular matrix, this is the LU factorization.
So how do they get there?
Okay, we're getting to that.
Okay,
We're going to get to that. This is just showing you what an upper and lower triangular matrix being a product to give you that. That's the factorization, LU factorization. Okay. Now, they do one a little more complicated. Here's the A. It's a 3 by 3. 1, negative 3, 0, 0, 1, 3, and 2, negative 10, 2. Okay? Now, without telling you how they got it, they claim that this is the product of 1, 0, 0, 0, 1, 0, and 2, negative 4, 0. 1, 2, negative 4, 1. Times, that's a lower triangular matrix, the L. The upper triangular matrix is 1, negative 3, 0, 0, 1, 3, and 0, 0, 14. Now again, they didn't tell you how they got it. They just said, here's an upper triangle, a lower triangular matrix. There's an upper triangular matrix. Let's multiply them and see what we get. Okay, here we go again. Plus is 1. Is negative 3. And 0. Okay? That row worked. Let's see if the next row works. 0. Yeah, that one worked too. Let's see if the next element works.
0, 1, 0.
Yep, that worked. Third one.
0, 3, 0.
Okay, 3. Okay. And the last.
2, 0, 0.
2. That worked.
0.
Ah.
I can see. Oh, negative 6.
Negative 6.
Negative 4.
Okay. Negative 6 plus negative 4 is?
Negative 10.
Negative 10.
0.
Negative 10. And the last one.
0. Negative 12.
What's that?
Negative 12.
Negative 12, you said?
Yes.
Okay, I can't hear.
And 14.
Okay.
2.
2. There you got it. Now, again, they didn't tell you how they got it.
That's what I'm concerned about.
Okay. What's that?
That's what I'm wondering now.
Okay.
They just guess numbers until they get it, or did the system to get it?
Okay. What do you think? You think if you just guess the numbers, you can make it work every time?
Not every time, but you can, but you gotta be there a long time.
You got to be there a long time guessing. Okay. So there should be a system. That's what we're going to do now. How are we doing on time? Oh, we got 10 minutes, don't we? Okay. Now, before we get there, linear algebra applied, there's one at the bottom. This is computational fluid dynamics. I don't know if any of you are going into that, but this is used all over the place, especially in things such as what they used to call wind tunnels, where they test, say, a car, an airplane, anything else, and study the dynamics of the fluid, air, or if it was a boat or submarine, water, whatever it happened to be, and study the dynamical situation there. Linear algebra is how you do it. So if that's an interest of yours, that could be a potential paper topic. All right. Now, I think I'll do a little writing here and then I'll erase it right before. If a square matrix A reduces to an upper triangular matrix U using only the row operations of adding a multiple of one row to another row below it, then it is relatively easy to find the LU factorization of a matrix A. All you need to do is keep track of the individual row operations as shown in this example. So let me do what they say. Here, this is showing you how they got these. So let's start with the matrix A. And that's going to be 1, negative 3, 0, 0, 1, 3, 2, negative 10, 2. Now, if you hadn't noticed it, this is the same one we started with before, but that one they just showed it. Now we're going to see how to get this. Okay. Now, what I'm going to do is start with, and I've started doing this. The book doesn't do it. It seems like it was just such a simple thing to do. Let's start with the identity matrix of the same size here. What would that be? 1, negative 3. Oh, wait. Huh. I'm writing the same matrix again. Sorry. 1, 0, 0. You're right. Okay. 1, 0, 0. 0, 1, 0. 0, 0, 1. Okay. You don't have to write that. They don't. But to me, it's easier to follow. Okay. Now, to get a lower, an equivalent matrix that is lower triangular, upper triangular, okay, all you do is row reduction, right? That's right. You want a 1, you have a 1 there, you want it there, okay? You got a 0 there, you want a 0 there. All you got to do is do this. What operation will change that? Negative 2, row 1, plus row 3. Okay? Now let's do that operation down here. You're using row 1, so write it down. 1, negative 3, 0. Okay? You're not doing anything to 2, so leave that alone. 0, 1, 3. Okay? And do this operation here. 0. Nope. Okay. Negative 2 times negative 3 is positive 6 plus a negative 10. Negative 4. Perfect. Okay. Next. It's what? 2. Good. All right. Let's do those same operations to I to get your what we going to call E1. This is very similar to what we did in the couple of examples ago. Okay. Only this is a 3 by 3. Okay. Now we're doing this operation, these operations to the identity matrix. Pretty simple. Top 2 rows stay the same, 1, 0, 0, just like they did before. 0, 1, 0. Negative 2. Zero. 1. Perfect. Okay. Now, what's the next step you want to do to reduce this A to make that lower triangular? 4, row 2, plus row 3. Okay? And what will that result in? 1, negative 3, 0. That doesn't change. 0, 1, 3. That doesn't change. 0, 0, 14. Okay. Now what elementary matrix does the same thing? Now this time be careful. Okay. We're doing this operation to the identity matrix, not to the one next to it, the identity matrix. What would that be? Back to the identity matrix. But do that operation to it. So in other words, the top 2 rows stay the same. 1, 0, 0, 0, 1, 0. I don't think so.
Oh, we do it on the second row.
No, doing it to the third row. Yeah. 0. 4. 1. All right. All right. Now, the reduced matrix here is an upper triangular matrix, right? Now, flip back a page and see if that's the upper triangular matrix we wound up with in the B part. Yes, perfectly. Exactly the same. None of you have pages to flip back, do you? Okay, sorry. Okay.
I did flip the page.
Oh, yeah.
Memory
Spiritually.
page.
Okay,
Memory
all right.
we just did.
All right. Now, what we need to do now is that's upper triangular. It follows, okay, now what we just did is that we started the matrix A, we multiplied it by E1 on the left, then we multiplied it by E2 on the left, okay, and that gave us our U matrix, right? This upper triangle that we just got. Because these elementary matrices would have done the same thing that elementary row operations did here. Remember, that's the definition of elementary row matrix. It does the same thing as that. So now we've got the first operate on A with E1 and then with E2, so do it in that order. Now, if you take this one and multiply, yuck. Okay. I think we're out of time, aren't we? Yuck. We were so close. But what you need to do, and I meant to be doing it as we did it, just like I did with Terrell earlier. I'm sorry I put that there. It's important, but we should have been doing the inverse matrices at the same time. So E1 inverse, can anyone tell me quickly what that would be? Terrell should be able to. I know it's coming. Okay. 1 0 0 0 1 0 2 0 1. Okay. And E2 inverse? 1 0 0 0 1 0 negative 4 1. Perfect, perfect, perfect. All right. We'll start with that next time. We'll have to go back and we're not going to reproduce all this, but we'll get to this point and we'll go to town with that. Okay? So, let me figure out exactly where on the page we are then. Okay? Right there. Okay, we haven't multiplied yet. Okay. So we'll start right there. Now let's see if we got far enough to get any homework exercises. I'm sure we did. We almost are through with this section. We're going to finish it next time for sure. Do any of the odds 1 through 7, 9 or 11, 13 or 15, 17 or 19, or 17 through 21, 23 or 25, any of the odds 27 to 33, and you should be able to do 35. 37 possibly, 39. You can start trying to do 41 and 43, but we'll get that next time. Okay, good deal. Have a good weekend, and we've just got one more section to do, but we're not going to do the whole section. I'll try to have your test ready for you next time, which means I need to get those first tests in. Okay? Have a good weekend. All right.
Bye, win.
What's that?
So what are we going to do about the whole tornado thing? Or,
What's that?
I said, what are we going to do about the whole tornado thing? Or
I'd check at the front desk and see if they've heard anything. They usually